There we go.
I
Yes,
was
it's recording.
Okay.
Afghanistan.
Any questions on the assignment?
6.
Wait, question or problem?
Problem, not question. I had no problem.
He doesn't have any questions
Well, I
about the
asked you to
questions.
wrap
He
up
only
six.
has problems about the problem.
Oh my gosh.
I have a question about the problem.
It's already recording. Okay.
I know, I'm trying to,
Alright, I was just making
I'm
sure.
trying to get the top
You
of it.
didn't turn off the recording before we even get to the solving part of this all.
Okay, so
So you can see the board.
it's funny, last year when I assigned this problem, I just had this procedure done because I was having some back pain, so I knew exactly how this was going to play out. So you've got ultrasounds, okay, simplify the reflection is one pulse should be received before the next is transmitted. The system is being used for an image 12 centimeters below, which is about like yay. Then, what's the minimum time between pulses? How many pulses per second does this correspond to? Okay, so what you've got to do is that, so here's your surface, right? And here's this ultrasound machine. And it's going to send out this signal. It's going to hit a bone, something like that. And then it's going to bounce back, okay? So at the end of the day, this is basically, to a certain extent, distance equals velocity
Okay,
times
well, I
time.
found the answer to I was informed the answer to the question. I was asking about
He
the
didn't
speed of
see. He didn't see the little table of
On 4
Yeah.
7 4.
values.
So you got to go to table 15.1 and find the speed of sound on an ultrasound machine is 1,540 meters per second. Okay? Notice that that is about 5 times faster than the speed of sound in air.
It always moves faster through a solid,
Yes.
but and through a liquid. But
And so sound, air is actually the slowest one if you look on there, okay? So, and we're always going to use like 343, unless I tell you differently, use 343 as the speed of sound in air. So, you're going to go to that human tissue, find you got 1540. So here's what's important though. It's got to travel 0.12 meters down and 0.12 meters back up, okay, before you send out the next one. So basically, you're going to use the idea that distance traveled equals velocity times time. So your distance isn't going to be the 12 centimeters, it's going to be 24 because it's got to go down, hit that, and then come back out. So, in terms of the period should be something times 10 to the negative fourth, okay, on number 6. And then the pulses per second is like around 6,000. Which is, I mean, if you consider like 6,000 pulses per second, that's a lot, okay?
I can't count that high.
No, you can't,
Well, you could just take you a while.
yeah. Now, on number 4, because notoriously number 4, sometimes this gives you trouble. That the pulses are separated in time by 11.0. So on number 4, you've got 11.0 ms. Okay, what's the M going to stand for? Milliseconds. Okay,
Yes.
right. Just like if it's 11 millimeters, there's 1,000 millimeters in a meter. With this, there's 1,000 milliseconds in a second. So, anyway, if all goes well on number 4, because if you look at what's happened, it's got to hit, okay? And then on the other end, you got to figure out that time. So if all goes well on number 4,
Where'd you get
your
78?
speed should be around 6,000 meters per second. Okay? That's an ish, but it should be around 6,000.
Oh wait, the distance is
You made it too fast, Mia.
Yeah.
You're speeding up the speed. That's not
Well,
how.
so did you.
No, but I multiplied the final
Your answer to number 2 should be
multiplied
around
times.
100.
because it's gonna take twice as long to come. Okay, I'll come back.
yeah,
What?
like the thing is, so, what kind of answer are we looking for at number 4? Sorry, I was focusing on number 6.
Around 6,000.
Yeah, I got that.
I read this as
Anything else? Going once? Going twice? So,
That was the first time we didn't have a lesson in
6,000.
Otherwise I'd put right
Did I mess that up? 4 divided by.
May I soldier soldier big demon from Bangladesh.
Man, not again.
Have fun with
How's that
that.
6,000?
The demon also has autism. Yes, that
Ryan.
Andrew,
Now it's a.
Andrew,
Yes.
could you imagine interacting with an autistic demon?
I choose not to.
That would be hilarious.
Alright, 6,000. How did that happen?
I only have 3 computers. What did I do wrong?
What did you do for number 4?
Would it be
That's the same that I got.
40%?
So what did
Ryan, how did you do number 4?
Because we both got the same answer, but it's not
Which is
6,000.
wrong.
Okay, how did you do it?
We took the distance divided by time. Times velocity.
Fine.
I'm assuming that's not what it was asking.
No.
What was it asking then?
It was asking. It was asking you to calculate. I don't. Be honest with you. It was asking you to calculate the velocity for this. So you have to basically.
What is the speed of sound in the metal?
Yeah, use this. Okay. What?
Oh, we use the speed of air. How long it takes it to travel in air minus that. Then we find it.
Yeah.
But I solved it before realizing that the other thing was wrong. That's what I did.
Okay,
Yeah,
so
basically, so you subtract the amount of time it takes to float. You subtract like the 0.0 milliseconds from the time it takes to travel through air, and that will give you.
okay,
Me working 30 hours.
Yes, sir.
so today we just kind of, it's kind of, well, that in fact a bunch of people gone, so, anyway. So we got some kind of refresher of what we did yesterday, but also some new stuff in terms of like intensity, and then decibels and how sound is measured, and then we're going to finish up with like the micro effect. So, in fact, what time do you guys have to leave?
225.
Okay, yeah, I'll be done. So here's like, this is what we talked about yesterday. So here's kind of the mother of all sound equations. The velocity is going to equal the wavelength times the frequency. Sometimes you see this as lambda nu. So if you're talking about any form of electromagnetic spectrum, whether that's radio waves, and here's a common misconception that everybody tends to get on. So if you're listening to a radio wave, okay, a radio wave, they're not transmitting sound, okay? It isn't like, if you're listening to a radio, no, I'm serious, everybody screws this up. Because, I'll say, a radio wave is being transmitted from, a station in downtown Wichita. How long is it going to take to get out to Mays? And everybody's going to try and take, and they're going to try and use the speed of sound, because it's a radio wave, as 343 meters per second. Don't laugh. I've done this for 30 years now. It happens, okay?
Be honest with
And you all sit there and go, Mr. Burkamp, we won't do that. You lie. Okay?
Be honest with you. Really, just call it radio light.
So, whether it's radio waves, whether it's microwaves, visible light, X-rays, gamma rays, doesn't make any difference, okay? Any form of electromagnetic radiation is going to travel at 3.00 times 10 to the 8th meters per second. We're always going to use the speed of sound as being 343. Now, here's something new that we need to introduce. And this is this concept of intensity. So, intensity is power divided by area. So remember, power is measured in watts, okay, which is technically joules per
Second.
because it's work divided by time. So when you're talking about intensity, that's watts per square meter. So this is important in terms of radio signals, in terms of light, whatever it is. So, and trust me, if you're on this side of me and this side of this projector, you understand this equation very clearly, because that's a very, very, very bright bulb. And so if I get really, really close to that bulb, guess what?
Your eyes don't feel.
Yeah, the power is going to be a fixed value, right? But if I get really, really close to it, then what's happening is that light is spreading out. So as that light spreads out, it becomes more and more diffuse. If I'm back here, the power coming out of the bulb is a fixed value. But as I get further away, the area over which that energy is spread has gotten bigger, so what's happened to the intensity?
It's decreased.
It's decreased. And that's true whether, if you're talking about, let's say for example, you light a candle, okay? Well, if you put your hand right there beside that flame, what you're feeling is electromagnetic radiation. You're feeling infrared. So if you put your hand right there beside that candle, it feels really, 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 really hot because it's emitting that power, but it hasn't spread out very far. But if you move your hand back, as you move your hand back, it feels less warmth because of the fact that the same amount of energy is being spread out over a larger and larger area. Same thing is true of solar panels. Okay, hey, we're on Earth. We are getting a certain amount of solar radiation from the sun. Okay? Nice. Now, if I'm on Venus, which is closer to the sun, that light's going to be more intense. So those same solar panels on Venus, to get that same amount of power generated, I wouldn't need as many solar panels because the light's going to be more intense. Now, you get out to Mars. Okay, Mars says, oh, we'll go to Mars, which is cool, and it does. It sounds cool. Okay, let's colonize Mars. Well, even if you want to use solar arrays on Mars, guess what? You're a lot farther from the sun, so to get that same power generated, like if I have that same solar array out here as I have on Mars and I want to get that same amount of power, guess what's going to happen? Yeah, I got to build a much bigger array on Mars to get the same power that I'm going to get from this solar array right here. So there's any number of things that's going to impact. So if you've ever gone old school and like actually listened to your radio, okay, and let's say you're driving out and let's say you're listening to a station here in Wichita. As you drive further and further and further away, what's going to happen?
It gets quieter and more staticky.
Yeah, it gets quieter and more staticky because the radio station is still transmitting that same amount of energy, but that energy per square meter is becoming less and less and less until you can't pick up that signal anymore. Okay? Yes, Mia?
Is it an exponential decrease?
Yes.
Or it is.
Because it's area, so it's r squared.
Ah.
Okay? All right. So, speaking of which, so there's two ways you can talk about this area calculation. One, if it's a plane wave, okay? So in other words, this is like you're just transmitting signals from like a single point source like a radio signal. Then that's just, that area calculation is pi r squared. Now, if you're talking about a sphere, okay, let's say for example I've got a light bulb, okay? So if I've got like a light bulb and that's emitting light, then that's emitting light in a three-dimensional space. It's like you're trying to eliminate a sphere, which would be like a candle, a light bulb with sun, for example. Okay, that's emitting light in a spherical direction. So a sphere is, you're going to use 4 pi r squared. Okay. So these are the two ways that you're going to calculate this area. So here's what's going to be important. Notice that, and this is what me had asked about, notice that they're both r squared. So if you double the distance, what's going to happen to your intensity?
It's going to quadruple.
You know, if you double the distance, well, if you double the distance away,
Oh.
It's gonna,
yeah, it'd become a fourth. If you become twice as close, then your intensity is going to go up by a factor of 4. Now, so a lot of times what you want to do is like a ratio. So let's say that you have, here's your source, okay, right, and it's emitting some type of radiation. And that intensity at the source is 10 watts per square meter at a radius of 1 meter. So what I want to know is what's going to be the intensity if I back up to 4 meters. Okay, so now we're going to go further away. So here's what you want to look at. This is like a ratio of I1 over I2 is going to equal,
1,600.
so then this, don't write all this down. I'll tell you what to get to, which is going to be the nuts and bolts.
Yes.
Don't write all this down. I'm just showing you a bunch of math. Or if you really want to.
Yes. Oh, I get it.
The source. Yes.
Sphere.
Not a sphere, that was a circle. It's area, not volume.
He didn't really do it. That's what matters.
Little did you know.
My grandma does too. You're fine.
Is it 4 pi r squared or pi r cubed?
She got a cat, she got what?
But a cat. And she can't keep it. She knew she couldn't keep it.
Of all things to listen to in this conversation. I just Benji watches soap operas.
Because here's what I heard. True story. This is why I normally tone things out when I'm in the zone. I swear to God, this is what I heard. My grandma got a cat with no feet. Okay? That's what I heard. So, that's why I'm going, let me get this straight. Grandma got a cat with no feet.
The cat has feet, as far as I know.
But she can't keep it.
So does anyone want a cat?
That has feet. It sounds like a Dr. Seuss thing going back. Grandma has a cat that she can't keep, but it has feet.
The cat hat was a little too
1
annoying.
feet,
It's not a
2
new
feet,
album,
3
guys.
feet, 3 feet.
The red foot loop.
Okay,
Crimson.
sorry.
What's the cat?
It's just, that's what I heard, and,
Name the cat that has 3 feet. Name the cat that has 3 feet yardstick.
Okay, but here's the difference. You spend
Say again?
Are there cats?
Okay, I'm gonna be honest with you. I have vague memories of me like going to my grandma's house and she's like just she can't speak
I can't
English.
remember if there's monitor or
So
not.
us two
There's a
sitting
little
on
black
top
cat
of
that
it.
rides a broom around in his winter
I feel
hat.
like
I need to
a
find
lot of
this.
just like-
Can't remember that was modded though.
okay.
So nothing compared to like Hispanic.
So, here's the nuts and bolts of this whole bunch of math that I just worked out. Okay? And hopefully you should be able to look at this and know, oh, this makes sense. So, basically you're comparing, like for example, here's the source of sound, light, it doesn't make any difference, okay? Because it's watts per square meter, okay? So, let's say that if you're 1 meter away from the source, this is the intensity, 10 watts per square meter. So what I want to find is the new intensity if I'm 4 meters away from there. Okay, so I've quadrupled my distance. I've gone from 1 meter out to 4 meters. So this is just a ratio. So, hey, I want to find this ratio of I1 to I2. So if you actually go through and if you wanted to calculate the actual intensity, okay, if you actually wanted to calculate the intensity, this would be the power at the source. Because of the fact that we're assuming that it's going to be emanating out in a circular path, this is going to be 4 pi squared R1 squared. And then the second intensity is going to be the same power of the source, which is going to be the same, 4 pi squared R2 squared. Well, because of the fact that all of this is going to be the same, the power from the source, the 4 pi squared, and then I've got R2 squared in the denominator, this thing is going to flip up, so it becomes I1 over I2 is going to equal, that's an R2 squared. Kind of important. Okay? So that's going to be R2 squared over R1 squared, which is where this comes from. So then, if you just do some simple cross multiplication, and hopefully, you know, this should make sense. So, if you look at this mathematically, there's this looking equal sign in here. So, I1, right, is going to have a really intense sound, or light, whatever that is, but you're going to be really close to it. Out here, I2 is going to be much smaller, but you're going to be much further away from it. Okay? So that's the importance of that equality sign there. So then, if you want to solve for that in second intensity, oh, here's my first one. So basically, you're going to take 10 and you're going to divide that by 16 because of the fact that it's 4 squared. Oh, okay. So it's going to be 1/16 as much. Boom, I get 0.625. So if you were to look at this, and goes back to what Mia asked about, and say, okay, well, let's look at a graph of intensity versus radius. So if we were at 1 meter, we had an intensity of 10 watts per square meter. When we go out here to 4 meters, that's dropped down to 0.625. So what's that graph going to look like? Yeah, right? So it's going to produce a swooping line like this because, so as you get close, it's going to get really, 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 really loud. So this is why when you all go to rock, and we'll talk about this in just a second, when you all go to rock concerts, so we go, oh, let's go by the stage, let's stand by the speakers. Okay, remember this curve. Okay? When you all want to go stand by the speakers at a rock concert, okay? Bad things are going to happen when you get really, really close because of the fact that you're going to have a really, really intense sound level based upon that proximity.
But you also don't want to be too far
So
away.
we can calculate the optimal position to be in a rock concert.
Ooh, yeah.
Well, kind of, yeah.
At
It
home
depends
it's
on
different though.
it depends on how loud you personally
Now,
want your music
speaking
to
of
be.
sound,
It's different at home though. If you get to a certain point close enough to the speakers, like just between them, you can't.
Right,
It doesn't
'cause it goes
affect
behind you.
Yeah, it pretty much goes through.
Well, but they're not facing
Yeah.
this way. So they're emitting this way. It's like that. It'd be like, here's the speaker, it's going to go out.
And then here's another speaker. And then here's the DJ.
I mean, you'll still be able to hear it
It'll
because
be
they're
like-
compression, right? So they're going to compress this and it's going to come out like this. But there's also going to be some coming back this way.
Yeah.
But not as
You can
intense
hear
as
it, but it's not near as loud. And it's actually a lot better than being that middle of like
I'm
the
going
throng.
to assume that it loses intensity over time based on friction.
Not to mention all the massive bodies just impeding.
Yeah, because when a wave goes from one material into another, it loses some.
Wait, wouldn't that mean sound would travel faster as it goes through people?
Technically, yeah.
Would but it wouldn't keep its intensity going through people.
Decibels.
Yeah.
Is that beta?
No, it's decibels.
It's the D-dollar.
Oh, you mean B? The B? I have no idea.
That looks
Bruh.
like a beta.
Might be, or might just be coincidence that you drew the line of
It's
it.
B for boy.
It's B for boy. Stop me alone.
Bruh.
okay,
You're missing out, Aaron.
so this equation, it's not on your equation sheet, but it's just kind of like a general science.
Pain.
Oh yeah, that's the pain threshold. It's the
So
Oh no, he's going back to that.
what this calculates is sound level. So first off, notice this is like a log value. So, and I will always give you this, don't memorize it, you just have to know how to use it. So it's 10 decibels times the log of I over I naught. I naught is like the lower absolute threshold of being able to hear anything, which is 10 times 10 to the negative 12th watts per square meter. So this is going to be the intensity of what you're actually hearing. So clearly, as this intensity becomes bigger and bigger and bigger, you're going to be taking the log of a number that's bigger and bigger and bigger. The decibels are going to go higher and higher and higher, right? So this I naught will never change. This is like the constant. So the only thing you can change is an intensity up here. So this is a chart that's in your book. It's chart 15.3. Okay, it gives the intensity and the decibels at different values. So normal conversation, and I'll show you this in just a second, is about 60 decibels. When you cross the threshold of pain where it actually hurts, that's like 130. So let's go to the back and let's kind of see where we're at with sound.
We're gonna definitely.
Are you gonna cut it to 130?
It only needs to go. It only needs to be 85 to damage your hearing. It just only starts hurting at 130.
Because our eardrums can't sense pain? Or
No, it just starts like it does. It starts doing damage in the 85.
huh.
It just doesn't start doing much.
They're both grandmas.
It's like karaoke.
Really?
Okay, quiet kids, time to shine.
Alright.
Mr. Bergkamp's gonna
Quiet
say.
kids.
We only have 2 of the 3 though. Tate's gone.
Yeah, where is Tate?
I don't know. Cool Tate left.
Huh?
Cool Tate left us.
No, Cool Tate says
Cool Tate as opposed to lame Tate?
No. Cool Tate as opposed to the other Tates in this school. Because the Tate in this class is Cool Tate.
She called him Tate, and then he goes. So she committed to die.
Liza.
Okay.
I can't be the only one.
So now let's just, because if I just sit here, right, with no noise at all, we drop down to about 55, okay?
Seriously?
Yeah,
Well,
Yeah.
I mean, there are noises.
yeah, I mean, there's
going
some
on.
background noise and things like that.
I
okay?
think a squeaking right
Now-
now. Lost it.
So if I hold this here and I go, ah, okay, that got me up to about 89. Now, Liza, you hold that over there. Okay. Now if I do that same thing and go, ah, okay, I only got to about 80. So why did that decibel drop when she had that further away?
Because the intensity was less.
Yes, because of the fact that as that energy got spread out, it's an exponential function in terms of, that intensity is going to drop further and further and further. So if I want to try and peg it out, okay, so I'm going to hold this close, right, and I'm going to yell, okay.
Coach Bergkamp.
Coach Bergkamp.
I gotta get my, hold on. Can you just, hold on.
What was it?
It was 99.
Impressive.
Not
Mia, can you break Brian?
What was it that
To
time?
95.
98.
I can break that easy.
Can you break the pain threshold? Here you go.
I got my.
Probably.
Do it.
Oh, he
Okay.
beat you right.
I'm in
Just
character.
scream.
All right.
Moonhead, what are you doing? And so,
Someone's gonna come in
watch
wondering what the heck you're yelling about.
huh?
Someone's gonna come in here.
Oh, they're
and
not
be
gonna
like,
care.
"What
They're
is he
just gonna go,
yelling?"
it's Burkamp.
We just have to get the
It sounds like an explosion happened. This room could seriously explode and no one would question it.
I mean, my mom questioned it when she heard the 80s
Maybe at the
music.
end of the day, people might go like, where's Burkamp in this kid? Just a random explosion, no one's gonna care. Okay. So just random yelling. Okay. So,
Certainly
all right, so
not.
we go. All right, people, you drop it, give me 20! 97.
I got
Okay.
99 on that.
Okay, not bad.
Right?
So here, choir kid,
Oh.
Yes!
Oh, boy.
Yes!
Just yell anything.
yell anything.
Close as possible and as loud as
Yell
possible.
Chicago.
Well, no, no.
Cool tape.
No, you're so
Cool Tate!
Where's Cool Tate? I don't know where he went!
97.
Yeah, 97.7.
97.
Yeah, that's
Anyone
not
else want to
bad.
scream? Get out some
Anybody else?
anger.
I think
Mia. Oh,
Okay,
me,
someone
come
needs
on.
to take this.
Catherine? Oh, cameraman. This is my future career, guys. Any tips?
loud, not pitch.
Yeah.
Don't kill
What do you
us.
mean
Use
don't
your
have
It
like
isn't frequency, it's amplitude.
But my
Diaphragm.
but my amplitude is highest at.
Okay, all right, Cookie.
God, what was that? 98.
That hurt!
Sure that wasn't one.
I was like so aggressive.
Yeah, Ryan got to 99.
How did he beat me?
Ethan, I know you can yell.
That
He said it hurt.
But it's only with language, like,
Keaton, can we get?
if I get really mad, I will yell really loud.
We give you permission to drop as many F-bombs as possible.
Said that in a long time.
Keaton.
Good?
Yeah, we're
Please.
talking
Good?
Keaton.
Scream.
Okay, anybody else want to give it a try?
Pineapple.
So I need to get this mango out?
Bruce.
Bruce.
What would I say?
Come on, Bruce.
What would I say?
Yes, it's just sing a Bruce Springsteen song.
Born in the USA.
Scream.
Yeah.
More than you.
Born in the USA!
We got 98.7.
Oh, you hit
Yeah, we got 98.7.
That sounded so much louder than Ryan though.
No, yours was still louder, Mia.
Yeah.
But I was less than Ryan.
Well, because it's a bad sense of
So everybody kind of get close. We do a
It
quick
hurts.
sure you got
scream.
1 to 130.
So we'll yell
It hurts.
AP Physics. Okay?
Okay.
On 3. 1, 2, 3.
99.
Oh my
We
god.
only matched Ryan by himself.
We just passed Ryan by. Okay. All right, we're good.
That was fun.
That's our battle.
That was fun.
That's a little bit.
Everyone in the game
My
right
throat stings now. I have regrets. I know.
My band can't voice.
Did you enjoy that screaming, Aaron?
And Tate. Can't forget Tate. Cool Tate.
We don't care about you, Tate.
I do the plug. Move it the camera.
What are you speaking?
I don't know.
Well done.
Oh, please tell them to wear headphones at the beginning of this video, please.
Oh. No.
He'll catch on once he gets to the screaming part.
Ooh, fun. Oh, I didn't get to. Oh.
What do you need?
The beta.
Right there, man.
Oh, okay. Thank you.
I also have the constant written down.
I've done that.
I over I not. Did you write down what I not was?
Yes, I did.
Okay.
I bet if Mr. Burkham had said you can't crack anyone's chest, you would have screamed like 130.
Oh, yeah.
Oh no. Someone's got
How did I not write 130? That's my question.
It's not bad.
We should have put it on like record mode so that we can see the peaks.
Oh, that would have been nice.
Because then we could have seen.
I could probably do it again if you want.
No, I'll pass.
100 decibels.
It is still okay.
It's 10,000 times louder than normal conversation.
What is?
The normal conversation.
What is?
100 decibels.
That's what you can call me grandma.